Please do check. Finally, we request the online audience to keep their microphones on silent for the duration of the talk. And for questions, you can unmute yourself and ask directly or post in the chat box so that we can relay them. Over to you, Professor.
No, this is when a size is moved out. Yes. Good evening. First of all, I want to thank the organizers for the invitation to give the talk here. So in this talk, I'm going to present this work on clustering of data streams, where each data stream is from some unknown IID samples from an unknown distribution. So that this was work with my PhD student Sreeram, who graduated last year. So let's first look at what the problem is. So here the problem is each vertical stream here is a data stream. So it's IID samples from possibly from some different distribution, each of them. So the job is to group these streams into clusters so that and the way and basically what we want to do is if their distributions are close, we want to put them in the same cluster. So that is the basic task. But we don't know what the distributions are. We are going to estimate from the samples that we see, and then we have to cluster these data streams into groups. So each stream is IID samples from possibly from different distribution, and the distributions are unknown, but we have to cluster based on the underlying. So another way you can think of it is each district. So here each point is some distribution, and depending on the distance between some distance between distributions, you have to group them. But according, this is also called, I think, distributional clustering. So basically, we have some finite number of data streams, and let's say for most part, we will assume that the number of clusters is known. There is another variation where you don't know the number of clusters, but you need some other information about the size of the clusters. So that I will mention in between. And there could be the number of distributions could be different in each cluster and all that. There is no restriction on it. So you could have multiple streams from the same distribution, or each of them could be different and all. But for now, we have a finite number of streams. We just have to group them into clusters.
What is there are two subscripts which you have, right?
So here the subscript is the cluster number and the number index within the cluster. So 2-1 means this is second cluster.
You're saying that there M1 distribution in first cluster and M2 in second cluster.
Not so important that notation.
So the cluster number is different than the total data. Oh, so you're saying M1 plus M2 plus whatever.
All of that is S.
Is equal to S. Okay.
Or need not be S, because multiple data streams can be from the same distribution. Total number of distributions is 3. So that is the problem. So typically, you can formulate it as a hypothesis testing problem. That is, you have to associate a cluster index with every stream, and there are so many ways of doing it. So it's a hypothesis test problem. So if you know what are all the possible distributions, but you don't know which stream is following which distribution, then you can calculate some likelihood. Take every stream, decide which is the distribution according to the likelihood. And if you don't know the distribution, but you have some model, let's say you know that they are all Gaussian, but you don't know only the mean, then you can extract. That's a parametric model for the distributions. So there, typically, what you can do is you can estimate the unknown parameters and then substitute it in the likelihood and get the generalized likelihood and decide based on that. So in this talk, we are not going to have this. we don't have any particular model for the distributions. So that is why we call it non-parametric. There is no finite number of unknown parameters. So the distributions could be some arbitrary continuous. And so here we are going to, what we are going to do is we are going to estimate some kind of distance between data streams. So here in generalized likelihood or likelihood, typically some tail divergence distances will show up. So one way to do it is to estimate tail divergence and do the clustering based on that. But that's not the way we are going to do it here. We are going to use two other, mainly this, I will talk about only this maximum mean discrepancy. We have also done using this other method. So the reason for choosing is, actually we could consider using KL divergence, but I'll say something about that at the end. But the reason for choosing the other two are that they are easier to estimate, and since we also want to do sequential setting, we want to be able to estimate, update the distance immediately when you get additional samples. So that is one of the reasons for doing this. So in the most of the talk, I will be talking only about these other two distances, MMD and KS distance. So the estimates will be based on the samples, and there are, the reason for using them are that they have good properties. The estimates have good convergence properties, and sequential update is also possible. So let's just, I won't get into too much detail, but just briefly introduce what is this maximum mean discrepancy. So basically, I want to compare distribution P and distribution Q. So you just find expected value under P and expected value under Q and look at the difference. Now you can choose any function that you want here and try to see if you can use that as the distance. And here we are following some method which was proposed here. So one of the main advantages of that method is that the F is chosen such that this metric is, this is like a metric. It will be this, and this is 0 only if P is equal. So anytime P is not equal to Q, the measure will not, this distance will. So that is something that you want to ensure when you, right? Because you can say one, like you can have first moment and second moment to be the same, but still the MMD will not be 0. GP not 0 as long as there's some P is not exactly equal. So that is one thing. And also it turns out that this is easy to, this is somewhat easier to estimate. I will show the estimator in the next slide. And that estimator also has good convergence properties. So
how do you discover for this RPHs?
So that is a prop that, why, how to choose it is not, is discussed here. So we have just chosen whatever they chose as the kernel and the function. But we have not worked out, there is no contribution from our side on that. We are just reusing it. So as I said, there are some conditions you want, how you want the distance to behave. So based on that you can. So of course you have to choose the F to somewhat maximize this. The class of F is also important, but finally you have to have some tractable method also. So everything. So they have suggested one thing which they use for what is called a two sample test. Two sample test is basically you have two sequences. You have to decide whether they are from the same distribution or from a different distribution. So for that problem, they have introduced this method. So since this is more general than that, but finally it comes down to comparing distributions, we are using the same approach. So for it, so now basically here is an estimate of that minimum MMD square. MMD, if you square root of this, so you can think of it as estimate of the square of the MMD. So it is basically, these are estimates of second moment. Each term you can see is some expected value of some second order terms from the samples, right? So this is one estimator, and basically what happens is they have already proved in that paper that if you use this estimate, it is a biased estimate, but if you look at the difference between the estimate and the true true value, the probability that it is greater than this root k by n comes from the bias. So the bias goes down as 1 by root n. And then, so if you look at this probability can be bounded exponentially, right? So as n increases, it will go down exponentially. So this is that is the property. So we are actually using this property in our proofs also. Everything relies on.
So the assumption is that the ith is from P and jth is from Q, whatever.
The assumption, yeah, we have two sequences, one from P and one from Q. Actually, here I have shown everything with same number of samples from both distribution. But all this can be generalized even if the number of samples is not equal from each string. But since I am not discussing that case, I didn't want to introduce that.
So you're saying that
you could have m samples from one distribution and n samples from another. There will be a slight change in the formula.
That expectation fx minus expectation fy written, that will turn out to be this.
That will. This is an estimate of that. So there will be some expected value to get that, but we are replacing the expected value by the empirical estimate of that. Basically, that's what it was. You have to simplify that to some expected value formula and then substitute the expected value with the empirical estimate.
So there is no square inside the assumption, right?
There is no square. But these are all second order calculations, and so it's an estimate of the square of it.
Can you go back to the definition of f?
F here I didn't. So it's some function chosen from a.
So do you have fx or fx square now? Because you said the square distance will be what you showed us is square of.
Yes, that is the square of the final.
The total square.
Yeah. Okay. So all that plays a role in simplifying and getting this formula.
So actually,
how you choose the f, how you right? But I didn't want to get into that because that's not our actually focus. So we have the main thing is you have to have an estimator which has such convergence properties. Only then we can show the result that we want for probability of error of clustering.
The f is not arbitrary, it's tied to this k.
Yeah.
This particular concept.
Yes. So of course here also there are multiple choices possible. We have just pick one thing which works from that case. So this is for the MFD. And you can also do some sequential.
That's one more question. I know it's not main focus, but somehow the soup of f just showed up as in terms of this kernel, right? Because your f was in this entire.
It depends on what you choose your class to optimize over.
Right.
So that is since that by fixing that properly, you can get a solution. That's what they showed in that paper. It's not a short answer. It's involved to show that by doing this, you can get what you want. That is there in this paper. So you can see that this kind of update can be converted to easily. So if I have n-1 samples, I have some distance estimate, square of the distance estimate, how to get if I get one more sample from each stream, how to update it. So it is actually, it's not that complicated to do it. Because, so the calculations are like order n square calculations here. And here it will be, the extra calculation will be of order n for every new sample. So that is something that we want also, that we want to update the distance sequentially. So that's one of the reasons for using. The other distance is this Kolmogorov distance. So this is basically, you look at the CDF, two CDFs, and look at the maximum absolute value difference between the CDFs. So, and you can estimate this using empirical CDF and also show some similar properties for this. So here also they are actually, you can show that.
So Ij is the stream I, stream j?
Yeah, if I want to compare stream I and stream j, I just find the empirical CDF of I, empirical CDF of j and compare.
And
And
this
this
is
is
how you
just
update.
standard update of the particular CDF. And this also has a similar properties. There was a bias term, here that is also.
This is much easier, right? Because this is some law of large numbers.
That's also actually finally proved using something like that. Okay. So anyway, that is just a few slides about why we are using that distance. Now, what are we going to do with that distance measure? And basically, we are going to do the clustering using that distance as the measure, and we are going to try to see what is the probability of error. So the error means if there is some under, let's say you know the two distributions and you have some true clustering, you have to get exactly that from the samples. Even if one stream is classified wrongly, it is called an error. So we are going to look at what happens to probability of error and how it decreases with increasing number of samples. So that is what we call consistency. Consistency means probability of error should go to 0 as number of samples increases. Exponential means it should go to 0 exponentially, and the rate at which it goes is error. But we won't discuss much about exponent today. We're just going to consistency here. Because we are just going to bound it. That bound may not be the actual probability of error. In fact, in simulation, we see that the actual performance is better than the bound. So it is not there. So so first let us talk about the case where the number of samples is fixed. So let's say you have n samples from each stream, and I have to do the clustering. So here is a method which is from this paper. So first, what you do is you first estimate the pairwise distances between all the streams. Then you are going to use those pairwise distances in a clustering algorithm. So there are many possibilities there, but here what they have done is using what is called k-medoid clustering. I will talk about what that is. And basically, you have to construct it such that you can get finally exponential consistency. That is the goal. So to get that, you have to show that whatever method you choose there can achieve that. Right. So this clustering will have there are multiple methods discussed here. First is, as I said, we focus on when the number of clusters is known, what will you do? And then if the number of clusters is not known, I will briefly tell how it can be modified. And then each of these clustering involves like an iterative algorithm, which will start with some centers and then form the clusters and then iterate till it converges. So let's look at the method. So first, as I said, is computing the pairwise distance estimates. Right, we don't know the exact distance. What we have is the estimate between streams. So the way the initialization is also actually very important. The initialization is done this way. So first you pick any one stream randomly as one center, and then the next center will be the one that is farthest from that stream, right? And then the third one will be the one which has minimum distance to the already chosen centers. So you keep picking like this till if you want k clusters, you find k centers, right? So this is the initialization. So I have to do this max min distance based initialization, and that is the starting point. Is that clear?
What does medoid do?
Medoid is like I will tell you what. But at least what is the definition here? That it's not like the mean is just the average. Medoid is one of the points. It cannot be anything else. So you have to find the one which has where the sum of the distances is minimum to the other points. So it is like the center, but it is one of the points. So it's like median, but it's the center point in some sense.
So you choose k center from the start.
This is the initialization. First you pick based only on the distance. Now your clustering has not yet happened. Only the center.
But initialization is that critical? I mean, you could have done that also.
No, it is important actually. We have to, at least in this consistency, it won't work if you change it. Because the error probability at each step has to be good. You have to start with a good center. Then, what is the clustering? What is the k-medoid clustering? So basically, what you do is now that you have the centers, you look at each string and find out which center is the closest, and assign that string to that center.
So in this setting, you already have entire string data, right? It's post factor. You're not doing online.
Yeah, we have n samples from each string, and we calculated the distance based on distance estimates based on the n samples. Now, if I have sequential problem, there will be, suppose I get one more string. Now I have to go and update all the values and then repeat.
Got it.
So first step is obvious. What you do is you take each string, put it in the cluster for which so that it is closest to that center, right? That is what you will do obviously. So that is the first step. Now we have clusters, but now we are going to update the center. That is the only that's the only medoid step basically. So what you do now?
Fixed sample size.
Right?
The sample size for each string is fixed.
Is fixed here right now. So that is this end. So now, how do you update the center? So now let's say I have these three sequences in one cluster here. So I'm going to now compare sum of so I'll take the distance from 1 to 2 and 1 to 5 and add, and then I take the distance from 2 to 1 and 2 to 5 and add, and so you just do the sum of distances from each. If one was the center, this will be the distance of all the other points to the center. You add them all up, and then you choose the one which is the smallest. That is the k-medoid clustering. So you do that. So now the centers would have changed after doing this. So now you repeat so you go back and do the clustering again. And then you keep iterating between the two till there is no change in the. If there is no change in the center, that means it won't change after that. So you are done. So you have to repeat the center and the cluster update till there is no change. So that is basically. So what they showed for this method is that if I do clustering this way, the probability of error of clustering is actually goes down exponentially in n. And that is the result from this page. So what are these? I guess some of these terms. The m actually is the total number of streams here. T is the number of iterations of that clustering algorithm that was done. But they have also proved that T is finite. It will not be infinite. So T is finite. So and K is bound on the kernel. So if you use the Gaussian kernel that I wrote there, K is 1. You can. So K is just the bound on the kernel. So everything is constant. So it goes down exponentially in n, and this delta square. So here what we have is we have something which is a difference between distance. I will explain what this is in the next slide. So what is this constant delta square that comes in their analysis? So that turns out to be. So if you think of the clusters and the distances, so you take the maximum distance between any two distributions in the same cluster. That is dl, and the minimum distance between any two distributions in different clusters, that is dh. So for their analysis, what is needed is that the maximum distance between any two sequences from the same cluster is less than minimum distance between any two sequences in different clusters. Right, so under that condition only that analysis works. And the difference between this DH and DL is that theta. And that determines, that comes here. But of course, as I said, this is only a bound. So the actual probability of error may be better than this. So this is what comes from the analysis. But there is no guarantee that this is actually a type bound or actual performance. So so here only thing that it shows is that it is exponentially consistent. The error exponent it gives, so here that it basically depends on, for this analysis it depends on the difference between DH and D.
The error here is you're misclassifying one of the clusters.
Any
Any
the clustering should match the underlying. If that does not happen, it's a so this is what happens in the fixed sample size study. So you can do exponential consistency with the MMD distance and K-MEDOT test. If you put all these together and you go through the analysis, right?
What is the complexity of this?
Complexity is in terms of which parameters. So if you have the number of streams,
Sample size.
yeah. So the estimate of MMD is like order n square.
Yeah, then you have to do all kind of distance.
Distance also is pairwise. So if the number of streams is some number, it is the square, right?
Maximizing minimum distance and all that.
Which one? The initialization.
Also the update.
Yeah, but those are small. I think actually the main the clustering part is everything is so actually the computing the pairwise distance itself is more complex than the cluster. So if you have lots of streams, then first you have to go and
All the pairwise distances are computed once and that's it. After that, you don't go back to decompute. Is that correct? Between any pair of streams.
but if you have more samples, then you have to recompute.
I mean, online setting, but fixed size is done, right? S square.
Yeah, degree of the order. So S square distances you have to calculate, each of them is n square.
So S square, N square.
The meaning of the concept. Everything has to be done in the concept.
Yeah, clustering has some iterations, but that is some finite number of iterations. That will depend more on the, but that is similar. I don't think it's more complicated.
No, but in that depends on the T, right? How many iterations? Because whatever you do, you have to do it every time till it converges, right? 3 times same operation. Find the center,
Right.
which cluster you like, right? Again, repeat 3 times, right? So each iteration, what is the complexity?
But it's all limited by the number of streams in one cluster. Whereas the original thing is square in the total number of streams.
So it's S
The
kind.
original thing,
Computing the value is quite complex.
pairwise numbers. Quadratic numbers.
So I don't think there's anything else to be worse than similar. It's there in the paper. I should not explain. But here I'm not focusing much on the computational aspect, but there is some. But the pairwise distance is itself. So you may not have to do pairwise distance. Every pairwise distance to start off. That is also a problem that we have. I'm not talking about. So this is what is there for fixed sample size. So what you can also use this result actually to get a sequential method which is also exponentially consistent. But in there, what it means is the probability of error will go to 0 with the expected number of samples exponential. So that is what we did. But we are using the same same pyramidal idea. I will talk about some other clustering at the end. So if you don't know the number of clusters, what can you do? So the thing is, if you don't know the number, you still need to have some idea of what these clusters are. So here there are two methods that they have for unknown number of clusters, but they actually have information about the size of the cluster. So you have to have some idea of before you can decide whether your clustering is right to decide what is your cluster. So you cannot, if you don't know this and you don't know the number of clusters, then you cannot do it. There's nothing to tell you whether you have something reasonable or so. So either you can provide information as number of clusters, or you can say what is the approximate size of the cluster also. And based on that, you can again come up with an answer. So when you have some idea of pH and DL, so actually what they use in the algorithm is the average of pH and DL, or some linear combination. So they have some variants. I don't want to get into that, but you can, if you know DH plus DL by 2, you can derive, you can show that these other variants are also exponentially consistent. So there are two ways. One is start with some big cluster and then split if you think it's too big, because you have some idea of pH and DL. The other approach is to start from small clusters and then merge them till you have
only get an idea of pH and DL. It's not like that. It doesn't come from the underlying model.
that is from your whatever application you're trying to use, you should have some idea. Okay. Because otherwise you don't know where to stop cluster. You can always say every string is one cluster. That is the one extreme. So how much? What is in that? I mean, for every application, what is reasonable grouping of distributions is up to this function of the application. But what are these distributions actually close or not? I mean, it depends on what you are using. So in their paper, they also have these two variants for which there is exponential. So if you want to do a sequential now, so let's just use the same method. So I know how to do it for n samples. So first you do it for n samples. Now I have to suppose I get one more sample from every stream. How do I change this solution? Right. So first, for calculating the pairwise distances, we have some sequential update for the pairwise, which is easier than starting from scratch. So I can now do order n calculation to get the updated distances, and then I can run again the k-mirror test. Now, so in the sequential setting, the other thing that I have to decide is now how many samples is enough. Right, so we observe one sample at a time, and I have to at some point I decide that that's it. I don't need any more samples. So we have to see what is the probability of error for that. So the stopping rule that we have two changes now. One is update the pairwise distance as the samples come, using that sequential update, and then you have to have some way of deciding when to stop, and that is going to be so I'm going to compare this. I'm going to compute the minimum intercluster distance of what I have as the current solution. Right? I'm going to compute the minimum take two different clusters and find the minimum possible intercluster distance for our final clustering solution. And then I'm going to threshold that. But the threshold is going to start from something high and then go down. And this clustering, once the minimum distance exceeds this, once the minimum intercluster distance exceeds some threshold, I'm going to stop. But I'm reducing the threshold as I get more and more samples. Okay. So the thing is, you have to choose this so that you get consistency and whatever. So that you can prove consistency. So for that, we had to choose this C by square root of n. So initially, we had tried some other
So what is the intuition you are going to get? So initially you said that DH and DL should be somehow given by the application, right?
No, right now we are back to let's say, so you can either do this with number of clusters known or with DH plus DL by 2. One of the two pieces of information. So that you know when to say that you are.
But now you're coming up with a rule to stop, right? This is
Stop is here. I'm getting one sample. First, I get one sample from all streams, and I'm getting more and more samples. I want to say that if I'm at some point we stop, and
I don't want any more.
yeah, at some point you have to decide what is your cluster with some probability of error guarantee ideally. But here we are just giving a way so that if you increase this threshold, you will get lower probability of error. And what consistency guarantees is there is some you can keep on increasing the C to get as low probability of error. So if you want smaller, you have to increase. So it will become probability of error will be a function of C. And if I keep increasing C, probability of error keep going up exponentially. So anyway, I will show some more details.
So why is stopping important? You'll continue, right? And you say like, if you keep giving me data, I can keep telling you what is the right class, right?
Yes, but I mean you can do that here also. I'm just saying that will the probability of error go down with time is money. When I have to stop at some point, it's expected stopping time. But when I have a sequential rule, how long I take to decide versus what is the probability of error. So when it's fixed number of samples, we look at probability of error versus number of samples. So equivalent formulation here is what is the probability of error versus expected stopping. So for each sample, I will stop at a different time, but on average, our expectation is that it will be better than using a fixed number of samples on average. That's typically the advantage of sequential over fixed sample rate is that you show that expected stopping time will be lesser than how many samples are required for a fixed sample case.
So you seem to keep going if your minimum distance exceeds the threshold and stop and it becomes smaller than the threshold.
No, when the minimum.
No, sorry, the other way around. That is, you keep going if the minimum distance is exceeding the threshold.
It's not.
No, it doesn't exceed the threshold. I mean,
Yeah.
it's below the threshold.
Yeah. If the clusters are close, I have to say how close they are. But I am changing that with them.
In the constant case setting, what is the closeness of the cluster? If you just want K clusters, closer they are, the better. Or if the cluster distance, if you want K clusters, what is better then? What is the good state? You know you want K clusters, right?
Yeah.
So then
I know, but I want to know. I want to know that these clusters are actually the clusters according to the true distribution. When I don't have enough data, actually my estimates of the distances are not correct. So even if I get K clusters, I am not very confident that that's actually the correct.
The quality of the estimates depend on the number of samples.
yeah, I know. Like, usually you would want to keep going if your estimates are not good enough. The question is what is the meaning of not good enough? In this case,
Yeah, here what I am saying is that I decide that it is not good enough this way, and this ensures that probability of error is good.
Somehow the intra-cluster you don't care about. It's only inter-cluster.
Yeah, for the stopping error. Of course, but the analysis also assumes that the intra-cluster is smaller than right. That is also there. So when I don't have too many samples, so my distance estimates could all be not good. So I don't want to set a threshold too small. So I'm not confident. So afterwards I am confident. When I
set the threshold small, you keep going. That's what I'm agreed with.
If you set the threshold small, so the thing is
threshold small, you keep going, right?
you will not keep going because the threshold is continuously decreasing. But the distance, intercluster distance is going to be this one, is going to reach the true intercluster distance.
If the threshold, for example, set to 0, it always hit the no. The cluster.
If you set that this threshold to 0, it will never stop.
Exactly. Right?
Yes.
So,
But you don't want
so therefore, like if it's very, very small, you keep going until
there is some separation in the clusters, because I know that there is supposed to be separation.
no, actually that's the issue. That's what I'm confused now about. So no, if the threshold were to be set to 0, actually, you will stop because you are actually you're hitting the yes condition.
You will stop, but if you stop too early, if you just stop with I don't want any samples, there will be a lot of errors. Your clustering will not be what you want. Right? So you have to use samples to get the true distances, but just enough so that you have a reasonable problem.
The probability of error will also depend on the C. So
Yeah, the probability of error depends on C.
if your C is 0, then the probability of error will be terrible. Stop with C.
C should be, but what we will say is that the analysis there, if you keep on increasing C, you will get lower and lower. Or the bound will keep going down. So
The game, in this, do you also change the number of iterations for the Leroy algorithm?
the number of iterations is the number it takes to converge.
It's the stopping time, right?
No, the stopping time is.
No, that is
okay.
different. This is the samples. Within for each sample, there's clustering going.
Oh,
Center
for
and
each,
cluster.
for each, you're gonna run that previous algorithm. So this
Cluster.
you have Tn for each n.
Yes.
So here, is it guaranteed that we convert? I mean, can have maybe going back and forth.
That center cluster update. No, I mean, at least that already shows in that paper that the number of iterations will be
finite. So what do they say? Finite almost surely or something? So
finite. T will be finite. So what we show, which is that given that the fixed sample size thing has already some properties, we are going to use that. But when we do the sequential, we have some additional problems to look at. So first, as I said, our stopping rule is basically minimum intercluster distance greater than some threshold is what we are going to stop. So what we are going to show first is that probability of stopping, the stopping time, probability that the stopping time is greater than some value n. We want to bound that exponentially, right? You have to find we have to choose some, it's enough if you show that for some n greater than or equal to n, right? So that is the first part. The way we show that is by splitting it into two parts, one where there will be an error at the nth step and one where there is no error in the nth step. So this part can be taken care of using the fixed sample size analysis. Whereas the other part, now that you don't know that, you know that the clusters are correct, but you are not stopping. So what is the chance of that? So that can be bounded using the properties of this distance. So basically, we are going to split this into two parts. One which can be handled by the fixed sample size analysis, the other which can be handled by some distance property and the appropriate choice of Tn. So our C by root n is because of that. So if by choosing C by root n and using the properties of that MMT estimate, you can show that the other term also goes down.
So what is En?
En is so let's say we have some clustering at the nth step after n samples, that is whether that is correct or not. So if there is an error there, that will be clubbed into this term. If there is no error, it will go.
En is the error in the clustering algorithm at n step.
After n samples. So this can be handled using the fixed sample size analysis, and this part by choosing the threshold and using the properties of it.
So En prime is that clustering algorithm did not make any mistake, but
you
stop.
But you stop.
You stop before.
But you don't stop.
No, you don't stop.
What the
Oh, you mean like
is not
the-
wrong, but it's not
You are going next step. You should not have gone.
So that will not happen because the estimates are good and so you have to use that somehow in this analysis. So I'm not showing how to analyze the last part, but it basically follows. It is some use of the estimate properties. So given some underlying truth, our estimates are going to become good, so it will not violate. It will stop. That is the case. But also it also depends on what threshold you put there. So just a combination of that. So if I put c by root n and it works. That's all. So this is the first step. So all that this shows that n will be finite with probability 1. And there is also this exponential increase. And then we use that in the error probability analysis. Now the error probability analysis is you have some clustering output when it stops. So let's call that C. These are the clusters, and these are, let's say, the two clusters. If they are not the same, it's an error. So, and this is for any configuration. And the worst case is whichever configuration gives you the maximum. So you have to show that this maximum is goes to 0 exponentially. So here, one additional thing is, so we get some kind of upper bound, which will depend on C also, and you can keep on increasing C to get consistency. So if you want smaller probability of error, increase. That's all. So that is how it works. And but we also have this only for some C greater than or equal to. That is enough to show consistency. So here there is a problem of choosing this CD also in the proof. So again, the analysis is by splitting into two parts. One which follows from the finite fixed sample size or the exponential decrease in probability of n greater than or equal to n. One of that is one term is handled by that. Then the other thing is you have an error and you have stopped. Right, you are stopping at too soon with an error. And if you are doing that, then then you can show then there exists at least two sequences which are there is at least one wrong. If you make an error, there is at least one wrong assignment of cluster. So then you have to show that cannot happen. That probability also that cannot happen based on the underlying again the underlying distribution and the fact the estimate is has some properties. So again, split into two parts and deal with that.
Sorry, so you're saying.
So there are two.
Yes, sorry. So you're saying you would not have stopped too early, right? That's the second.
Yeah, chance of stopping with error too early is going to be small because again it depends on choice of the threshold and the underlying distance estimate properties.
I think there should be no summation. Yeah, I think that's third one. Actually, solve subject.
Where?
P of En, no? When you put summation in.
Yeah. There could be some. I mean, I just put this.
Oh, no, but maybe you're right. Actually, it's correct. Yeah, it's correct.
This is okay. So it boils. So we have to reduce it to. So what is the chance that there are two sequences in the same cluster, but you have stopped? So it will reduce to that, and that will not happen. Again, you can show that. So these are the steps. Now you have to convert that into a result like this, which can be that is not too complex. So again, as I said, the two main choices that we have to make here are for what n and c can be. We have to find some n and nb and cd so that all that thing works. So that the expressions for these and
So
not
ND was
there are some fixed.
ND was clear that what is CD?
CD is like this is the value of C beyond which this bound holds. That's also some bound, but some.
Sorry, what is C? What is C here?
C is part of the threshold. Threshold is C by root n.
C only.
So for C greater than some value, that bound is valid. So finally, you get something like this, which is the exponentially less. And here you can see that this constant depends on the square, pH square. But this bound is not right. The actual performance is better than.
Just from probability bounds, you came to the expectation. I can see that transition.
Yeah, here there is a jump. So from here, if you get to expectation, what we did show, I think I didn't put it here. So we showed that expected value of n by c minus some constant absolute value goes to 0, and then you have to use that to get this. So expected value of n by c will converge to some constant. That is one additional. So I'll just show some simulation results to end the talk. So here basically in all the simulations we have 5 clusters with 5 streams each. And there are 2 examples, one where every stream in the cluster has the same distribution. So there are basically only 5 distributions. Here they are all slightly different. Right? So for example, you can have Gaussian streams. Either each of them has different mean or there's some small difference in the means between the different streams of the cluster. Here this is some gamma distribution case. These examples we picked up from whatever already was there in the literature, so that easy to compare. So if you see what happens, this is minus log probability of error versus expected stopping time or number of samples. So if it is a fixed sample size test, this is the number of samples. If it is a sequential test, it is the expected number of samples. So, so if you see here, it shows all several things. So MMD, if you use MMD, you get some curves. Those are in red. If you use KS distance, you get some other curves. Those are in blue. Then fixed sample size is like dashed, and sequential is solid. So if you see here, red is generally better here than blue. So for this example, where we have the Gaussian distribution, this MMD, using MMD works better than KS distance. And then the 2 cases, this is the case where there's only one distribution in each cluster. This is the case where there are 5 distributions in each cluster. So this is okay. And fixed sample size is worse than sequential. Like sequential, you have to get some advantage because for some realizations you can decide easily. For some hard realizations, it will take more time. But on average, it will work faster than if you decide how many. So that is so fewer samples are required than a fixed sample. So this is one example. The other example, gamma distribution. So here the KS distance works better than the MM for gamma distribution. That same thing was observed earlier, so there's nothing more than. And then if you if you don't know the number of clusters, but you know DH plus DL by 2, then you can use that merging and splitting in this. And you can get similar results. Basically, this is fixed sample size, this is sequential. And again for 2 cases. This is the single distribution, this is split by distribution. So I skip this. So there are some other small things that we tried, which is like, so each time we do this clustering after you get one more sample. So we thought if you initialize the cluster, you can take the output from the last sample and use that as the initialization. Instead of doing that, picking the centers according to that max min. So that we tried, but we don't do it always. We do it under some condition. So basically, we say that if the previous cluster had some property, I will reuse it. Otherwise, I will not.
What is that? We have your property.
Yeah, some we check whether the empirical DL is less than empirical DH. So here it shows the fraction of time that this is the fraction. This is how often you redo from scratch. So if C is very small, you will keep redoing it. But if when C becomes larger, you will do it less. And similarly, you can check what happens as you get more samples. So what you see is that after you get sufficient number of samples, you will reuse the old cluster and not repeat start from scratch. But this is only a simulation study. This is not for the analysis. It relies on the original method. But in simulation, we saw that this also doesn't affect the performance much. As long as our empirical condition was okay. But that's only a simulation. And we'll skip the. And maybe I'll just say one thing about this. So one special case of this problem is anomaly detection. So let's say I have some normal data streams which have distributions that are close to each other, and then some few streams which have very different distribution. So here we are using this clustering to detect that. And basically, there's a comparison with two other. So the red curve is what you get from clustering algorithm. This better performance is achieved if you know the number of anomalous streams and use that specific anomaly detection scheme. You get better performance. If you use the anomaly detection scheme when the number of streams is not known, which is more like what is there in clustering, then that one doesn't work as well as the clustering method. And here it's actually the anomalies. There the anomalies are all following the same distribution. Here the anomalies can be different. So now you need actually more than 2 clusters to model it. And so the basic anomaly detection based method which relied on somehow implicitly on 2 clusters will not work. But this clustering method will work. So you just, and whatever is the largest cluster, we take that as the normal, and everything else is anomalous.
The left post.
Here, if you know that there are so many exactly how many anomalous streams are there, which to identify them, you can. That is the thing. And then the last thing is there is also a scale divergence based test, but this is only for discrete distributions with finite support. So we also compared our MMD based method doesn't actually use that information that the distribution actually takes only 10 pass, the random variable takes only 10 values. So here we compared the MMD based method with the KL divergence estimate based method. So the KL divergence based estimate method was better for fixed sample size than this MMD, because here we are not using the fact that there you are estimating this assuming that you know the support, but here we don't know anything about the support. But the sequential method was actually better than that fixed sample size. But this comparison is for an example that is there. And in this paper also they assume that they have the same DL less than DH. That is, any 2 streams from the same cluster are closer than any 2 streams from 2 different clusters. That assumption is there in this one. So we have recently also looked at some other clustering. So there is another class of clustering methods called hierarchical clustering. You start from, so one such thing is this linkage, single linkage cluster. Basically what you do is you take all streams as one cluster, and then you check, you merge the closest 2 into one, and then you have a way of merging clusters at each step. And at some point you have to stop. So to stop, you have to know either the number of clusters or your minimum inter-cluster distance. Otherwise, you don't know where to stop. You can just keep clustering till you get one big cluster. But you can stop at any level. So So what we actually in this those who did the K-Midot test, they also looked at some other linkage based, and for all of them they showed the same DL less than DH exponential consistency holds. But actually some algorithms can work for more cases than that. So that is what so what we showed is that one of these methods actually will work even if you have a simpler condition, which is, so now I need only the every distribution should have something closer in that cluster than any other cluster. That is the only requirement. The size of the cluster is not. You can have big clusters, but nearby. But as long as for every stream there is another stream which is closer in this cluster than the other cluster, that method will still work. So we identified that. But that's very recent. I don't have slides for that. So with that, I stop. So basically, I discussed non-parametric sequential clustering of data streams, and basically our goal was to get methods which are this universal exponential consistency problem.
Thank you for that, Professor, for an interesting and engaging talk. So please feel free to ask if you have any more questions.
So one question, do you assume the samples come at the same rate from all the end strings?
Right now, so yeah, we are taking one sample each from every stream. That is the setup.
At every instant of time, all the streams put out
one more sample. But you could extend it to. So the MMT estimates will work even if you have unequal number of samples from two streams. Of course, the properties will be slightly modified, but it's still a good estimates are there. Even if the number of samples is not exactly equal, the that estimator will work well. So as long as you have enough from all streams, you should be able to. They may be growing at different rate, but that might still be okay. That's what, but we have not analyzed.
Once you want to go back to the initial one, which the other team seemed to have done before you went to the sequential one. If you actually look at, you've computed all pairwise distances. Let's also look at fixed samples. Once you have the pairwise distances, you could also use other techniques like spectral clustering, etc. Because you have a full matrix of pairwise distances.
Yeah, but the thing is, what we want here is the underlying, there is some underlying distribution model, and we have to get that cluster. Yeah, I mean, there could be other clustering methods, but
the other clustering, I mean, if you go spectral clustering route, then you can look at the eigenvalues of the Laplacian and see how many are close to zero. That might give you some answer on the number of clusters and so on. So I'm just wondering if that was covered in that work. Or...
No, I don't think it was covered. But I think that here the basic assumption there is that the clusters are well separated. There, I don't know what spectral clustering may not be. I don't know what.
So, for example, spectral clustering might be useful in situations which violate that DHDL. But you mentioned towards the end something like if there is some neighbor which is close by in the same cluster that makes sense. For example, you have a cluster of big circle and then a small circle. And these are the two clusters. That will violate the DHDL condition.
Yeah, but I don't. Yeah, I don't. I mean, they have separated clusters. And our other result is only an initial definition. I have not thought about more complicated clusters. We have our examples still are separated clusters, but close but big clusters. Or one big and one small cluster. That is where K-Midot is not as good as linkage based, because Medoid by default it puts a cluster stream based on distance from center. So if you have a big one big cluster and one small cluster, it's possible that something in the small cluster is something in the big cluster is closer to the small cluster center. But if you do it based on the other linkage based, where you're only looking at nearest streams, then you will not put it in the wrong. So that's all that we identified. More than that, maybe if you have some other complicated clusters to start with, some other methods may be needed. Yeah.
If you go back to the expected value of the upper bound that you find, it was 1 by 2h squared.
Yeah.
That is not, I understand, but is there, so here, it has the correct form though, that there is log P.
Exponential form there.
That exponential form.
And some constant is there.
So if you want to understand what might be the best constant, the examples you had are all Gaussian families, so they are.
We have not compared with any other lower bound yet. There's something.
I was wondering if the
lower bound is.
If you work with Gayatri on exponential families, where once you
parametric.
have it, for the parametric.
Clustering, yeah. That again, there also we have to compute that bound and compare. For the clustering, it's actually not so easy to calculate that the nearest alternative is not so easy to calculate.
The nearest alternative should also be found based on the information which is available, which is DHDL bound. That I mean the DHDL.
Yeah, so I don't know for what case it's. I mean, it's to be done. Yeah, something that we have to do, but no answer.
Any more questions? Any more online questions?
We'll take it over after.
So yeah, we have arranged the refreshments at the coffee, right? So please feel free to continue your conversations there.